Welcome to all. So today we'll start the second lecture. In this second lecture, we'll try to give you a tool so that you can analyze any dynamic system subject to any event. Okay. So in this lecture, what we will be trying to do is that we'll be trying to give you a tool called equivalent static method, where by using this method, even if we have a very less knowledge of the dynamic principles involved or how to do the dynamic analysis, still we can analyze the system, get the response and then follow our design methods. So this is an approximate method which deals with the equivalent static analysis. So we will try to start this process. First of all, what we will do is that we will try to analyze using a proper single degree of freedom analysis. I will explain that, and after that we will see how the approximation works. So let us start the lecture. So we will start with the equilibrium equations. Let us say in real life scenario, we have a simple structure. Let us say we take a simple beam. Okay. So we normally take a simply supported beam. Okay. And we apply any loading, let us say F. So this is a time varying load F, and which has any arbitrary signature, does not matter. Okay. You can take any arbitrary signature. So this loading is changing with respect to time. So our system, our actual physical system is subjected to a dynamic loading. Okay. Now here, if we try to calculate the vertical response of the system, okay, if we try to calculate the vertical response of the system, let us say we are trying to calculate the vertical response of the system, and let us say we are interested in calculating the maximum response. Okay. So Y max. Okay. So if we try to plot Y max, okay, so if we try to plot Y max at x equals to a certain point, say x naught. Okay. So x naught is from here. Okay. So if you are trying to plot x equals to x naught, so what we will see is that our response is changing like this thing. Okay. And now using dynamic analysis, I have to calculate this Y max. So in order to calculate Y max, I need to have a knowledge of the dynamic analysis. So we will try to simplify this method. Okay. We will try to simplify this process. So what we will do is that we will take something that is known as a single degree of freedom approximation. Okay. Single degree of freedom approximation is a very neat technique where we can just calculate the maximum response of the system. Okay. So what are the fundamentals behind that? So let us say we have a system. Okay. So for any given system, in order to accurately draw the position of this system, okay, we will have independent unknowns. Okay. So this number of independent unknowns, are called degrees of freedom, and corresponding to each degrees of freedom we will have the associated frequencies. So for any given system, for any given physical system, we will have infinite degrees of freedom. That is, starting from this point, we need to know the deflections and the rotations at each and every point in order to draw the state of this system at any given time subject to any external forces. So when we start, we have infinite degrees of freedom. Let us say we have taken a very simple system, this simply supported beam, which is subjected to a loading at the center, a time varying loading at the center. So what is going to happen? This system is going to vibrate. So the vibration will look something like this in real time, and this will be the shape. Okay. This is a simply supported beam and the loading is at the center. So what we are expecting is that the maximum value of the deflection, the vertical deflection, will occur at the center. Okay. So the point we have identified that this location will be at the center. So this degree of freedom, the Y at center, becomes my chosen degree of freedom. Okay. So we have identified our degree of freedom. Next thing is the mode shape. What happens in any given system is that it is going to oscillate. So any given system will oscillate with infinite frequencies. Okay. So for this particular system, it will oscillate. First mode will be like this, second mode will be like this, third mode will be like this, and so on and so forth. And our final solution, the final oscillation of the system, will be a combination of all these oscillations. Okay, and so on and so forth. the magnitude that will be contribute to here will be varying. So, this will be contributing maximum, let us say 80%, this will contribute slightly less, let us say 6 to 7%, this will contribute less, let us say 6 to 7%, and this will contribute even less, maybe 1 to 2% and so on and so forth. So, the first mode, this mode will be contributing maximum. So, we will take this mode. So, this analysis where we are considering only one mode, this is called a single degree of freedom approximation. Okay. So, we are doing a single degree of freedom approximation. Okay. So, here what happens is that we will be ignoring the contribution of this mode and we will be ignoring the contribution of this mode and all the other modes. So, we will be only considering the first mode approximation. Okay. So, we will take this mode shape and this degree of freedom. Okay. So, once we have done that, so now our actual physical system from this single degree of approximation system, we will change this thing into this particular ice cream cart, where the total mass or the actual engaged mass will lump it, the effect of the stiffness will represent by a spring, and the effect of the damping in the system will be represented by this damper. Okay. And this will be my chosen degree of freedom. So, this corresponds to this deflection. Okay. So, this corresponds to this deflection. Now, our job is to calculate this equivalent mass, calculate this stiffness and calculate this damping. Okay. So, in order to do that, we will formulate what is known as equivalent mass, equivalent stiffness and equivalent damping. Okay. So, in order to do that, what we will do is that first we will formulate the shape function. So, we will write the shape function. Okay. So, remember what shape we took? We took this shape. Okay. For a simply supported beam, we took this shape. So, this shape, this particular shape we can calculate if we can put a static load P, and we know how to calculate the deflection when we are putting a load here. Okay. So, this is our static deflection equation. Okay. And we have chosen the degree of freedom at center. Okay. So, this y is at x equals to center or L over 2. So, we will again write the static deflection equation. Okay. And this one we will evaluate at x equals to L over 2. So, this becomes my shape function. Okay. And now I can write my equivalent mass as integrated over the entire length 0 to all L mass per unit length times phi square x dx. Okay. So, this becomes my equivalent mass. Okay. K also we can calculate in a similar fashion, EI integrated over the entire length, and similarly we can calculate my dynamic loading also. Okay. F equivalent dynamic loading equals to okay. So, what we have done is that we have taken our physical system and changed it to a equivalent single degree of freedom system. Okay. So, this much we can do. Okay. After that, let us come to the solution. So, here is the mass factor that will resist effect of the externally applied load, elastic system will be restoring force and C will be damping. So, let us say if we are ignoring damping. Okay. For this thing, let us say we are ignoring the damping. So, M becomes M equals to mass per unit length times phi function. Okay. My K becomes okay, and F becomes okay, and I got my equivalent mass, equivalent stiffness, forces, and we have ignored the damping. Okay. So, the signature of the system, so there will be only one frequency because we are only calculating the single degree of freedom system. So, omega n will be root over k over m. Damping right now we are ignoring. Okay, we will come back to this damping thing. Okay. So, let us do this thing without the damping, and once we are comfortable with this thing, we will come back to the damping. So, omega n corresponds to the free oscillation of the system. Okay. So, using Newtonian second law, we can write down the equation of motion for this system. Okay. So, remember we started with a simplified version of our physical system, then we changed this thing into a single degree of freedom system. From the single degree of the freedom system, using the Newtonian second law, we wrote down the equation of motion. Okay. So, this is the equation of motion in the second form. Okay. Let us say we want to put the damping also. Okay. So, let us say now we are engaging the damping. So, in civil engineering systems, what we do is that we write damping as a function of mass and as a function of stiffness. Okay. So, we always write down a equivalent damping. Okay. So, here we can see we have written down the damping. Okay. We have written down the damping as a function of mass and as a function of stiffness. Okay. So, this way we can include the effect of the damping also, and this is this guy. Okay. The damping ratio, this is the measure of the how much energy is dissipated in the system. Okay. So, now we have our equation of motion. Okay. From the physical system to single degree of freedom system to the equation of motion, and then the equation of motion in the standardized form. Okay. So, now if you look into this equation of motion, you will see, you will mark 2 to 3 things. Okay. Let us say that this external applied forces goes to 0. Okay. So, if it goes to 0, then we are left with okay. So, here this is a representation of the system. Okay. So, the system is represented by omega, that is the frequency, and the system is represented by the damping ratio. Okay. They in turn are represented by mass and stiffness. Okay. So, mass and stiffness becomes the fundamental properties. If we change the mass and if we change the stiffness of the system, then we can change the physical system. Okay. So, let us say we have M1, let us say we have M2, let us say we have M3. Okay. Let us say we have K1, we have K2, we have K3. So, these things are nothing but the representations of different configurations of beam. This might be a bigger beam, this might be a smaller beam, this might be a very thin beam. So, if we change mass and stiffness, we can have different configurations, meaning we can have different systems. So, frequency and damping ratio, they represent different systems. Okay. Remember this thing we will be using when we are talking about the equivalent static loading. Okay. And if we apply the force, the force will be causing the oscillations. Okay. So, we understood the frequency, we understood the natural frequency and the time period. Okay. Now, if we have the damping, so in damping we have 3 stages. Okay. Underdamped, where my damping is less than the critical damping, equally damped or critically damped, where the actual applied damping is equal to the critical damp, and overdamped system, where my damping ratio meaning the applied damping is more than the critical damping. Okay. So, this system will oscillate, this system will die down, and this system will not have any oscillations. Okay. So, let us try to solve a very simple case. Okay. Let us say we have been given that mass is 10 kgs, stiffness is 1000 Newton per meter, and there is a damping. Okay. So, the frequency becomes 10 radian per second and the damping ratio is 0.1. Okay. So, using these equations we have evaluated the system properties. Okay. So, here what we are showing is a representation of the displacement. Okay. the displacement of the system, whereas we are changing the damping ratio. Okay. Now, how we are getting these things? Okay. So, what we have done here is that in this thing the forces we have assumed as to be 0. So, this system is nothing but mx double dot plus kx plus cx dot equals to 0, subject to some initial condition. Okay. There is some initial condition. So, the solution of this becomes okay. So, this is the solution for this thing. Okay. And if you look here, okay, here we are ignoring the damping. Okay. If you ignore the damping, then this is my solution. And if you closely look here, A and B will be determined using the initial condition, but the signature of the system will depend upon the omega. Okay. So, this oscillations will look something like this. Okay. So, this will be the displacement of the system subjected to any initial condition. A and B will be given by the initial condition, and this omega will be dictating the frequency of the solution. Okay. Let us say that we introduce our damping. Okay. So, if we introduce our damping, then what will happen is that this oscillations, okay, will look something like this. Okay. Okay. And eventually they will die down. Okay. So, depending upon whether this is undamped, this is critically damped, or this is overdamped, you will have the signatures of the oscillations. Okay. So, this is what is shown in this graph. Okay. So, if my frequency is very less, you can see the damping ratio. Here you can see the effect of the damping ratio. Okay. So, it is less. Here we have increased the damping ratio. So, my system is dying out fast. Okay. And here you have a system where my damping ratio is more than the critical damping, and the system has just died down, there is no oscillation. Okay. So, my response depends upon the frequency of the system, it also depends upon the damping ratio of the system. Okay. So, this we are talking about the free vibration. Free vibration means the externally applied force is 0, the system is oscillating due to some initial condition. Okay. This much is okay. Okay. So, what we have done is that we have understood how the system will behave when it is subjected to, when the system is subjected to initial conditions only, there is no external forcing function. Okay. Now, let us introduce the forcing function and let us see how the system behaves. Okay. So, again the same thing that I was telling. So, this thing will be there, okay. This part will be there if zeta equals to 0, that is there is no damping ratio. This term takes into account the effect of damping. Okay. And this we called it as a transient response. Okay. If you remember your first year maths, okay, for any differential equation solution we used to have u equals to u complementary plus u particular. U particular where there was on the right hand side the value was non-zero, and when the value was 0 on the right hand side we only used to have u complementary. So, this was the mathematical representation, and this is the physical representation of this u complementary. U complementary means transient response, means this is the signature of the system. Okay. Okay. So, this is called the transient response. So, when damping is present, you will have exponential decay like this. Okay. The system is going to oscillate if the damping ratio is less than the critical damping, and the system will not oscillate if the damping ratio is more than the critical damping. Okay. So, we have covered the complementary solution or the transient response. Okay. Now, we will look into the particular solution. Okay. So, now we are looking into the steady state solution. Okay. So, it means that we are looking into the particular part of the solution. So, the particular part physically this is called the steady state response. Okay. So, let us say we have a harmonic type of loading. Okay. So, if we have a harmonic type of loading, then the solution for this harmonic type of loading will be this guy. Okay. And we can calculate the response of the system. Okay. Remember one thing, the total response of the system, okay, will be a sum of the complementary solution as well as the particular solution. Okay. So, let us say we have a system. Okay. Let us say we have a system. Okay. So, its total response u will be a combination of the particular solution and it will be a combination of the complementary solution or transient and steady state. Okay. So, this will be a sum total of this one u p and u c corresponding to a cos omega n plus b sin omega n t, this b sin omega n t times the e minus zeta omega n t. Okay. So, this will be the total solution of the system. So, the total solution of the system is shown in this blue ink. Okay. Okay. So, this is the total response of the system. Okay. So, what we have done is that we have taken a physical system. Okay. We said that the system maximum response will be at the center. So, we identified the degree of freedom. We took the first mode approximation. Okay. So, we took choose the mode shape here. Okay. From there we made our shape function. From the shape functions we calculated the equivalent mass, we calculated the equivalent stiffness, we calculated the equivalent forces and we evaluated the response of the system, the total response of the system, which is a signature of the particular part, that is the contribution from the external applied load, and the complementary part, that is the signature of the system. Okay. And we calculated the total response u. Okay. One small thing that is here. Okay. So, let us say this system was subjected to a static load. Okay. If the system was only subjected to a static load, then its u would have been, u static would have been just F divided by K. Okay. So, let us remember this thing also, we will use it later on. Okay. So, I hope we understood the system properties. Okay. Okay. So, now let us look into what the different parts like u particular plus u complementary or u steady state and u transient does on the system. Okay. So, effect of the transient responses, it reduces amplitude of the oscillation through damping or damping ratio, whatever you want to call it. Okay. Damping we are denoting by C. Okay. So, by using C or zeta. Increases rate of decay to steady state. Okay. If zeta increases, that is the damping ratio increases, the rate of decay also increases. Okay. Depending upon zeta, if zeta is more, then the decay is more. The signature of the system is given by the frequency, okay, which is a function of mass and stiffness. Okay. Energy dissipation depends upon the damping that is available in the system. Okay. Damping force always opposes the motion and damping is a necessary evil which is critical for the structural safety at resonance. Okay. So, damping is what that prevents the structure from resonating. Okay. So, effect of the steady state response, we have seen that steady state response comes from the externally applied forces, okay, that is effect of F naught. So, it limits the resonance amplification, it introduces a phase lag in the system because there might be a case where the externally applied load itself have some external frequency. Okay. So, this frequency omega is different from the structural frequency omega n. So, it introduces a phase lag in the system. Normally, the externally applied load controls the maximum response amplitude. Okay. Some of the damping values that we traditionally use for steel structure, the damping ratio is between 0.01 to 0.03, concrete structures 0.05 to 0.07 and rubber mounts or any elastic type of surfaces 0.1 to 0.3. So, here you can see material wise there is an increase in the damping ratio. Okay. Okay. So, moving ahead, here we are showing the effect of the damping which helps in reducing the transient oscillations and approach towards the steady state. So, higher the damping ratio, the system will easily reach the steady state. Okay. Now, we are introducing one term that is called as the dynamic magnification factor. Okay. So, let us go back and look into our equation once again. Okay. So, our total solution, okay. So, this part was the steady state solution, okay, and plus the transient solution will be E okay. So, this will be my total system response. Okay. So, here we can see it has 2 to 3 parts. In the first part, this one is governed by my damping ratio and my frequency. This part is governed by the amplitude of the forcing function f naught, okay. K is of course there. So, this part looks similar to the static deformation. Okay. So, the total solution u we can write as some function of u naught, a function of zeta and a function of omega n. Okay. So, the total response is function of the static response, that is nothing but the amplitude of the forcing function divided by my stiffness, function of the damping ratio and function of the system frequency. Okay. So, here we can write the total response as a function of 3 units. Okay. So, if we carry this forward, here this is denoted by u and this is the static part u naught. Okay. So, here it becomes a preliminary a function of my static response, my damping ratio and my frequency. Okay. So, this is the mathematical definition of the equation. Okay. So, if we look here, what we can say, we can call this thing as the dynamic magnification factor, meaning if we have applied a static load, if my system was like this, okay, and we apply a static load f naught, the maximum response will be u naught will be f naught divided by k. Let us say I applied a dynamic load out here. Okay. I applied a dynamic load and I again want to calculate the u max, okay, assuming my system is loaded at the center. Okay. Then the ratio of the u max, that is the displacement, maximum displacement due to the dynamic loading, and the ratio of u naught to the static loading, we are calling it as the dynamic magnification factor. Okay. So, this is nothing but the ratio of dynamic to static response. The amplification is due to the dynamic effects, and this thing can be used in the resonance analysis. Okay. So, this is the expression for the peak dynamic response. Okay. So, dynamic magnification factor, as you can see, if we decrease the value of the damping, okay, we will be able to see the resonance. Okay. As we increase the value of the damping, the effect of the resonance dies down. Okay. The frequency ratio, this is the frequency between the applied frequency by the external force, and this is the system frequency. So, as they try to approach unity, okay, there will be resonance in the system, and the maximum value of the dynamic magnification factor will be achieved at this point. Okay. So, here we are showing the increase in the dynamic magnification factor due to the resonance condition. Okay. There will be a phase lag in the dynamic response, meaning if there is a frequency in the system, okay, so the system is going to oscillate like this, okay, but there will be a lag if there is the external applied load is having a harmonic signature. Okay. So, there will be a phase lag between the force and the displacement, the externally applied force and the system response. Okay. So, mathematical expression for the phase lag is like this. Okay. So, if beta is less than 1, the force will lead the displacement. If beta equals to 1, force and displacement are 90 degree out of phase. Beta greater than 1, force lag the displacement. Okay. So, this is important for the force transmission. It affects the power requirements, and it is also critical for designing the vibration and isolation systems. So, this is the effect of the phase angle versus frequency ratio. So, you can see the change in the phase angle with respect to the frequency ratios. So, as it approaches 1, as we saw in the last slide, force and displacement will be 90 degree out of phase. Okay. And if it is more, then the force will be leading. If it is less, then the displacement will be leading. Okay. So, I conclude this lecture today. Thank you.